What specific problem does the Deep Schema Grounding (DSG) method aim to solve in terms of visual abstraction understanding?
The Deep Schema Grounding (DSG) method aims to solve the problem of understanding abstract visual concepts by enabling vision language models (VLMs) to interpret and reason about visual abstractions in a manner similar to humans. Current VLMs often default to literal interpretations of images, failing to recognize the underlying abstract concepts, such as the structure of a maze, when presented with unconventional visual representations. DSG addresses this by utilizing schemas, structured representations of abstract concepts that decompose them into concrete visual components, allowing models to ground these components hierarchically in real-world images. This hierarchical grounding process ensures that the interpretation of abstract concepts is informed by the relationships and dependencies among their subcomponents, thereby improving the model's ability to answer questions related to these abstractions accurately. Ultimately, DSG enhances the performance of VLMs on visual question-answering tasks by providing a more coherent and contextually rich understanding of visual abstractions.
How does the proposed Deep Schema Grounding (DSG) method work? Illustrate step by step the three main components of the method as presented in the paper.
The proposed Deep Schema Grounding (DSG) method operates through three main components. First, it extracts schema definitions of abstract concepts from a large language model (LLM), which generates a directed acyclic graph (DAG) representation that decomposes the abstract concept into concrete visual components. Second, DSG hierarchically grounds these schema components to visual entities in the image, starting with more concrete symbols and using them as conditions to resolve more abstract components, ensuring that the grounding process is informed by previously established context. Finally, the resolved schema, which includes the grounded components, is used as additional input to a vision language model, VLM, during the question-answering step, providing holistic context that enhances the model's ability to reason about the visual abstraction. This structured approach allows DSG to improve the performance of VLMs in understanding and reasoning about abstract concepts in images.
Can you provide a detailed example demonstrating the inner workings of the DSG method, specifically on how it interprets and grounds the concept of a maze?
The Deep Schema Grounding (DSG) method interprets and grounds the concept of a maze through a structured, hierarchical approach. First, DSG extracts a schema for maze from a large language model (LLM), which defines the concept as a directed acyclic graph (DAG), comprising components such as layout, wall construction, and entry-exit positioning. For instance, the schema might specify that the layout is rectangular, the walls are made of coffee beans, and the entry and exit are represented by coffee cups. Next, DSG hierarchically grounds these components to visual entities in an image, starting with the more concrete elements, like the layout, and using them to inform the grounding of more abstract components, like the entry and exit. Finally, the resolved schema, including the grounded mappings, is provided as context to a vision language model, VLM, during the question-answering phase, enhancing the model's ability to accurately respond to queries about the maze, such as identifying clear entrances or exits. This structured grounding process allows DSG to improve the understanding of visual abstractions significantly compared to traditional methods.
What theoretical or practical benefits does the DSG method offer compared to existing vision language models, VLMs, in understanding abstract concepts?
The Deep Schema Grounding (DSG) method offers significant theoretical and practical benefits over existing vision language models, VLMs, in understanding abstract concepts. Theoretically, DSG utilizes schemas as directed acyclic graphs, DAGs, to decompose abstract concepts into concrete visual components, allowing for a structured interpretation that aligns with human reasoning patterns. Practically, DSG enhances the performance of VLMs by providing a hierarchical grounding process that first resolves concrete components before addressing more abstract ones, which leads to improved accuracy in visual question-answering tasks. For instance, DSG demonstrated a 5.4 percentage point overall improvement in accuracy for GPT-4V, particularly excelling in counting questions with a 6.7 percentage point increase, indicating its effectiveness in associating abstract concepts with specific visual entities. Furthermore, the method is model agnostic, meaning it can be applied to various VLMs, thereby broadening its applicability and impact across different systems.
How was the effectiveness of the DSG method validated using the Visual Abstractions Dataset, VAD? Describe the experimental design and the evaluation metrics used.
The effectiveness of the Deep Schema Grounding (DSG) method was validated using the Visual Abstractions Dataset, VAD, which consists of 540 visual question answering instances across 12 abstract concepts. The experimental design involved comparing DSG's performance against baseline vision language models, VLMs, and integrated large language models, LLMs, on this dataset. Each instance in VAD included an image, a natural language question about the abstract concept, and an answer, allowing for a systematic evaluation of how well models could understand and reason about visual abstractions. The evaluation metrics focused on multiple-choice accuracy, calculated as exact match accuracy, against the modal responses provided by 5 human annotators. Results showed that DSG significantly improved the accuracy of models like GPT-4v by 5.4 percentage points overall, with notable enhancements in counting questions, indicating that the hierarchical grounding and structured thinking process, facilitated by DSG, effectively enhanced visual reasoning capabilities.
What significant results were achieved with the DSG method on the Visual Abstractions dataset, particularly regarding performance improvements on different types of questions? What does this imply about the efficacy of the DSG framework?
The Deep Schema Grounding (DSG) method achieved a significant overall performance improvement of 5.4 percentage points and 8.3% relative improvement on the Visual Abstractions dataset, VAD, when applied to the GPT-4v vision language model. Notably, DSG demonstrated a 6.7 percentage point improvement, 11.0% relative improvement, specifically on counting questions, indicating that the schema grounding process effectively associates abstract concepts with concrete entities in the images. This suggests that the hierarchical grounding approach of DSG enhances the model's ability to accurately interpret and reason about visual abstractions, particularly in complex reasoning tasks that require counting and detailed analysis. Furthermore, the results indicate that the structured thinking process facilitated by DSG is crucial for improving understanding of abstract concepts, as it allows for coherent and contextually informed responses. Overall, these findings imply that the DSG framework is a promising solution for enhancing visual reasoning capabilities in models dealing with abstract concepts.